Hello, Mr. Almond here, and this is your Almond Cast on lipids. In this video, I'm going to dive a little bit into the structure of this important nutrient and its impact on your health. As a quick review, remember that lipids, also known as fats, are a category of organic molecule made up of carbon and hydrogen with a little bit of oxygen. Lipids are important in living things because they serve as a storage of energy, long-term energy storage. And they can act as insulation, which is important in terms of being able to regulate body temperature, particularly for animals like mammals who maintain a consistent internal body temperature. Lipids of all types are not polymers, so they do not have an unlimited shape. So even though there are many different groups of lipids with unique chemical structures, they don't have the same unlimited potential as nucleic acids and proteins. There are three major groups: triglycerides, which serve as an important nutrient, phospholipids, which we've already studied as part of the cell membrane, and steroids, one of which we've studied cholesterol, and others will come up later in the course because those are important hormones. To begin with, we're going to start with triglycerides and the component fatty acids that they're made up of. A triglyceride has one glycerol, which is a kind of connector molecule, which links together three fatty acids. Thus we get the name tri for three, and a glyceride being the combination of the glycerol with fatty acid. Triglycerides, although they're not polymers, are formed by the condensation reaction, the same type of reaction which combines together amino acids or sugar molecules to make protein and starch. You can see here on the left we have an example of a monoglyceride. There is a single fatty acid, and you can see that there is the hydroxyl group, the oxygen and the hydrogen, at one end of that fatty acid. Likewise, the glycerol has three carbons, each of which has and three hydroxide groups, one with each of the carbons. The condensation reaction will harness two hydrogens and an oxygen from those groupings of atoms, removing those to make water, and creating a new type of bond called an ester bond, which then connects that fatty acid chain to that glycerol. In this case, this fat molecule is now a triglyceride because each of those three hydroxyl groups on the glycerol have been replaced with this new ester bond, connecting each one to its own fatty acid. The fatty acids themselves are hydrocarbons. Those hydrocarbons could be made up of single or double covalent bonds. And the composition of single and double bonds is an important way that we can distinguish different types of fatty acids to each other. We classify those fatty acids with no double bonds as saturated fats. They're called saturated because they have the maximum number of hydrogens. What we notice is that every time a double bond is added, hydrogen atoms are removed. So saturated fatty acids have the maximum amount of hydrogen possible given the size of the chain. We could classify any fatty acid with double bonds then as unsaturated. It has less than the maximum number of hydrogens, and therefore it is not or unsaturated. The presence of these double bonds affect the shape and the melting point of the acids. On the left side, you can notice here saturated fats. They have no double bonds between carbons. Notice there is a double bond between the carbon and the oxygen, which was at the carboxyl end of the original fatty acid before it was combined to the glycerol. That presence of that double bond doesn't affect this distinction between saturated and unsaturated fats, because we're really referring only to the number of double bonds between carbons. When you look at the space-filling model here of that unsaturated fat, you notice that it's linear. There are no bends or kinks or twists to this particular chain. It is completely straight, as though the carbons are all lined up in a straight line. Saturated fats are going to be more noticeable in animal fats. So butter, lard, those are going to have a much higher percentage of saturated fat in them. On the other hand, unsaturated fats, the presence of the double bond causes a bend. Here you can see that this cis double bond, which is the naturally occurring type of double bond, causes a bend in the chain. And so when triglycerides have more bends in the chain, it inhibits the ability for those triglycerides to be able to pack as closely to each other, meaning that they can never solidify. And because of those bends and because the fat molecules keep moving, we see that it maintains a liquid at room temperature. And so oils are usually primarily composed of unsaturated fats. We can further classify unsaturated fats based on the number of double bonds that they contain. A monounsaturated fat would contain only one double bond between carbons. Polyunsaturated fats, however, would contain more than one double bond, so 2, 3, 4, or more double bonds. In addition to these three categories of naturally occurring fatty acids, there is a fourth set of fatty acids called trans fatty acids. These trans fats differ in the position of the hydrogen atoms that are bonded around the carbon-carbon double bond. At the bottom here, you can see this naturally occurring cis fatty acid. The cis fatty acid has two hydrogens which are both bound on the same side of the double bond. You can notice here that they're both above that double bond. As a result, when the carbon chain continues on, it bends downwards. A trans fat, instead of both of those hydrogens being on the same side, in a trans fat the hydrogens are bonded opposite of each other on either side of that double bond. As a consequence of the position of those hydrogen atoms, the chain remains straight, looking in the end much more similar to a saturated fat. These trans fats, which again are mostly artificial, are made by the hydrogenation of plant-based oils. This process began when commercially packaged foods that needed to be shelf-stable began to become more common. And food manufacturers wanted a way to be able to keep fatty foods preserved for longer periods of time. Now, the saturated fats, which tend to be associated with much better taste, are more expensive because they come from animals, while oils don't have as good of a taste and texture, but they're much cheaper since they come directly from plants. They can be harvested in much greater quantities for less cost. So as a way to produce the texture which people associated with saturated fats, the hydrogen atoms are chemically added onto oils, and when those oils are hydrogenated with those extra hydrogen atoms, the chains get straightened out because that hydrogenation doesn't maintain those bends, but causes them to become these trans fats. So when someone eats a trans fat, they're getting the taste similar to eating something that's maybe high in butter or animal fat. Think like different types of really savory fried foods. And it gives a much more melt-in-your-mouth type of feel. Very different from those plant-based oils. It was effective in terms of delivering the taste that customers wanted without the cost. However, in the time period more recently, trans fats have now been recognized as inherently unsafe. And they've been unsafe because of some of the nutritional effects noticed by diets that are high in trans fats. In thinking about that, we have to think about what's happening in terms of digestion, absorption, and then ultimately the use of these fatty acids as energy. The digestion and absorption of fats is relatively non-specific. The enzymes, these types of lipases that are breaking down these lipids, they're going to break off whole fatty acids off of a chain of triglyceride. And then those things are going to get either diffused or actively transported into the body, where triglycerides will then be reformed, where they can then be stored for energy use later. Because of the breaking and rebuilding of those ester bonds, it doesn't really matter what type of fatty acid is there, an artificial unsaturated fat or an artificial trans fat or a naturally occurring cis fat. Once a fat is a fat to the digestive system, and so it's all going to get absorbed. But once it's time for that fat to be used, those fatty acids are going to get broken down. And the process to break down those fatty acids is going to be specific to the actual types of fatty acids. There's a whole pathway, multiple pathways by which these fats can get broken down and used as a source of energy in cell respiration. And because there is a specific relationship between enzyme and substrate, your body can't simply switch out one fatty acid for another and expect your enzyme to still work. Enzymes are going to respond to particular shapes. And so because the shapes of these fatty acids, these unnatural trans fats are different, the enzymes responsible are not going to be effective at breaking it down and metabolizing it for energy. In addition to this problem of trans fats not being metabolized, they also have an impact on blood cholesterol. Cholesterol, because it's hydrophobic, can't be transported through the blood as it is. There's too much of a risk of cholesterol molecules clumping together and forming clots. So your body takes cholesterol molecules and attaches those to proteins, which act as a type of chaperone, which is dissolvable in water and will flow easily through the blood. There are two forms, common forms that we see circulating in the blood, low and high density versions of these lipoproteins. LDL is generally considered bad cholesterol because in this case, those LDL lipoproteins are likely to attach to the walls of arteries where they can clump together and form plaques. In contrast, HDL is considered as a good form of cholesterol because HDL helps to flush away and prevents the buildup of those fatty plaques on the sides of those arteries. Now, all of that wasn't always known. We took a long time in order to figure out that connection between trans fats and the potential for heart disease. In the meantime, you have an industry which is very protective of its use of trans fats in packaged foods and in cooking in restaurants. So in order to overcome those odds, it's necessary for scientists to be able to collect data, large amounts of data from many people over long periods of time, in order to be able to show at first that correlation and then eventually that positive causation between trans fats in the diet and the impact on heart disease. In the next set of data that I'll show you, this comes from a review article in the New England Journal of Medicine. Review articles look at many different studies to look for trends across the work of many different scientists, generally over longer periods of time. In this graph on the right, you can see a description of changes in cholesterol levels for patients who underwent changes in diet. In these cases, replacing saturated fats, monounsaturated fats, or trans fats with, or polyunsaturated fats, replacing any of those naturally occurring fats with trans fats. There was a mild increase in amounts of LDL, which is bad cholesterol, for those that replaced the animal fats with trans fats. But for those that replaced plant-based fats with trans fats, there was a huge increase in amounts of LDL. And so that's going to lead to likely a buildup of more plaques in the arteries, which can lead to heart attack and stroke. In addition to that, we saw an impact of trans fats on the amount of HDL cholesterol circulating through the blood. So more trans fats decreased the amount of good cholesterol that was circulating. This review also looked at the impact specifically on heart disease itself, not just on cholesterol, which is a precursor to heart disease, but the actual numbers of heart attacks themselves. And you can see across all of these studies, nearly all of them saw an increase in the proportion or the relative risk of cardiovascular disease for those who had higher trans fats intake. And then when they looked at studies that looked at the potential benefit to people actually reducing or pulling trans fats out of their diet, no matter what it is that they replaced those trans fats with, whether it was saturated fats, carbohydrates, or unsaturated fats, there was always a potential benefit to the likelihood of them being able to prevent the development of cardiovascular disease. But particularly when those trans fats were replaced with carbs or with plant-based unsaturated fats, that decrease of 10, 15, 20 plus percent represents a significant potential health benefit to the entire country. So through this, through data from studies like these, government began to take notice and understand that there was a public health risk to people continuing to consume these trans fats. And so, first at the city level, and then eventually states and the FDA began to outlaw by through regulation the use of trans fats in preparation of foods. And we've seen the amounts of trans fats in any packaged foods or cooking in restaurants decrease to near zero at this point today. That's your introduction to lipids. Thank you for watching.